Hi everyone, my name is Seung Hong and I'm a professor at Hanyang University, Korea. I'm happy to give my presentation, Integration of 5G and OPC UA for Smart Manufacturing of the Future. Many people must have already heard about Industry 4.0. Currently, there exist many different definitions of Industry 4.0, but I like this one. Here, Industry 4.0 is defined as everything connected to everything. According to the platform Industry 4.0, Industry 4.0 refers to the intelligent networking of machines and processes for industry with the help of information and communication technology. Industry 4.0 was initiated by the platform Industry 4.0 in Germany. To realize Industry 4.0 by 2030, the platform Industry 4.0 announced three interlinked strategies: autonomy, interoperability, and sustainability. This is the conceptual diagram of autonomy in Industry 4.0. In the Industry 1.0, two people meet together to accomplish a task. This is their dialogue. Do you speak English? Yes, I do. Who are you? I'm a drill man. What is your capability? I can drill holes with the following quality. Fine. Drill me a hole? Yes, done. But on the right side, we can see in the 4.0, two machines talk with each other. Do you speak Industry 4.0? Yes, I do. Who are you? I'm a drilling machine. What is your capability? I can drill holes with the following quality. Fine. Drill me a hole. Yes, done. So, communication among machines is the most important issue to realize autonomy in Industry 4.0. However, the communication system in smart manufacturing must satisfy latency, reliability, flexibility, and interoperability. 5G is an emerging key connectivity solution for smart manufacturing, particularly for these three main service categories. First, enhanced MBB with a peak data rate up to 10 gigabit per second, massive MTC with a connection density of up to 100 nodes per square meter, URLLC that provides a 1 millisecond user plane latency with greater than 99.999% reliability. With the next generation of industrial revolution, 5G's powerful communication capability will help make the factory's production system much more flexible, productive, and efficient. Now, I will introduce the OPC UA technology in smart manufacturing. OPC UA is one of the key technology to realize the smart manufacturing. OPC UA is an international standard, IEC 62451, to support interoperability and data exchange across the smart manufacturing system. OPC UA also provides functionalities, including platform-independent service-oriented architecture, information model, which can model various complex manufacturing data into an OPC address space, and flexible data exchange mechanism. Then, why do we need to integrate 5G and OPC UA in smart manufacturing? In smart manufacturing, all components of the process must cooperate and communicate with each other. So, a flexible, interoperable, and real-time communication network is essential. 5G is a promising technology because it provides low latencies and high data transmission rate. However, Pure data transfer is only one aspect of information exchange in smart manufacturing system. Another equally important aspect is data modeling and enabling interoperable among different components. During the last several years, OPC UA was evolved to support data modeling and interoperability. With the integration of OPC UA and 5G, high flexible and powerful connectivity fabric for smart manufacturing can be formulated. We believe that 5G and OPC UA will drive us into a new manufacturing environment where many production processes can be improved with less cost and more flexibility. In this context, we initiated a 5G and OPC UA pilot project. In the pilot testbed, we adopted a software-defined 5G solution as a backbone to connect heterogeneous industrial field devices. Also, we adopted the OPC UA POP-SOC to realize horizontal and vertical interoperability between field devices in the field layer and the entities on the upper layers. This is the 5G and OPC UA system architecture of the manufacturing system testbed we developed. In the field layer, robot and conveyor belt operate to realize the pick and place operation. In the edge layer, we developed a software-defined 5G solution to guarantee real-time and deterministic data transmission between edge and field layers. In the cloud layer, a web user interface provides monitoring of the operation of the manufacturing system. This figure demonstrates the actual lab-size experimental system to show how we implemented the hardwares of the whole system. In the field layer, two kinds of actuators, robot arm and conveyor belt, as represented by label 1-1-3. Here you can see one dash 1-3 robot and 1-2-3 conveyor belt are employed to execute the pick and place transport processes. We use the one Raspberry board labeled 1-1-1. This is the Raspberry board for each robot or conveyor belt. This is 1-1-2-2 for conveyor belt for each robot and conveyor belt to develop its operation control software and OPC UA POP-SOC. Besides, there is a far-away 5G module here, 1-1-2, for each robot or conveyor belt to realize a 5G connection within the connection with the edge layer. In the edge layer, a Linux OS-based 5G facility labeled 2-1, you can hear labeled 2-1 here, with a 5G configuration UI labeled 2-2. Here we can see the 5G configuration UI we set up, in which a software-defined 5G stack and an OPC UA POP-SOC were deployed to connect with the field layer. Through 5G and OPC UA wireless connection, an operation decision software and a database are implemented to manage operation and aggregate status data of field components respectively. In the cloud layer, level 3 here, is implemented on a NUC mini PC with Linux OS. Here, visualized web UI was implemented, which allows the system operator to monitor the status of the devices of the field layer. This figure shows the communication of system component through 5G and OPC UA. Components interact with each other through the 5G networking using publish subscribe mechanism of OPC UA to exchange the status data. This figure shows a communication of system component through 5G and OPC UA. Components interact with each other through the 5G network using publish subscribe mechanism of OPC UA to exchange the status data. Runtime operation status, for example, start, stop of devices are updated on their OPC UA information model. Combining 5G and OPC UA enable the interoperability between individual robot and conveyor belts and guarantee pick and place operation among them. In this test bed, we adopted OPC UA information model for robot arm and conveyor belt. The information model helped the achievement of unified data management and analysis of the proposed manufacturing system. Conclusion. In Industry 4.0, all components of the process must cooperate and communicate with each other. To achieve this, 5G and OPC UA will be the key enabler to fulfill the stringent communication requirement and information model-based data management. In this context, we developed a 5G and OPC UA-based smart manufacturing testbed. The testbed can be used for the best practice guideline and promote integrated 5G and OPC UA technology for smart manufacturing. Our 5G and OPC UA pilot project is unique in the sense that it is one of the early efforts to build a private cellular testbed supporting all 5G key features.